though we'll talk about some other things that will not be with them very briefly. So, I'll make sure I spell their names correctly. Okay. So I want to try to convince you that the study of dense and non-dense orbits is very fundamental. So I just want to start off with a self-map, a dynamical system. And I am going to define two sets, which I will claim to be fundamental. So I'm going to define the set of points that have dense orbits in this dynamical system. We're going to note that by dt, and then the set of points that have non-dense orbits. And so to talk about density, I need to put a topology on here. So once you have that, then you can talk about these two sets. Now, so once you have a topology, I mean, how a point behaves, or whether its orbit is dense or not, is a fundamental property of such a point in such a system. Okay. So the fundamental question I want to ask is about the sizes of these sets. Okay? All right. So let me just talk about this very briefly. So for dense sets, so now this is too vague. We just have a topology. I want to put on some more structure. So let's talk about dense points for a second. So what I'll do is I will let T preserve a ergodic probability measure. Okay, and then so this question is very simple because by the Birkhoff-ergodic theorem, the set has full measure 1, and then therefore this set has measure 0. And so I want to talk, and then okay, so one other things, of course, if I have different dynamical systems on the same phase space with the same measure, then I can take a countable number of those systems, intersect them, and look at their simultaneous dense sets, points which are simultaneously dense under the countably many sets, and that will also have full measure. Okay, so that's just very easy stuff. Okay, so that's just by Birkhoff-ergodic theorem, and now if we talk about non-dense points, these are a little more interesting. All right. So I'm going to give a couple of examples, and the reason I'm going to give most of the examples is we're going to need to know about them for the result that Vitali and Maffer and I did. Okay, so in terms of number theory, this is, I'm sure, just review for all of you, but let me just remind you, I can write a number, a real number, and I can just assign it to a matrix, this one, which is an element in SL2R mod SL2Z. Okay, and there is, from the 80s, there's Donny correspondence.
Jimmy, sorry, can I ask you a question?
Yes.
I'm really puzzled by that first thing. An ergodic probability measure might be a point mass at a fixed point for T. And then...
Sure, okay, sorry. Hmm?
No, it has to have full support.
It has full support. Oh, sorry.
Okay.
Sorry about that.
Fine.
Right, okay, so there's Donny correspondence, which tells me that if alpha, and I think Dimitri introduced this yesterday, if alpha is a badly proximal number, then what that says is that this matrix, which I'm going to denote by lambda sub alpha, that the forward trajectory of the geodesic flow in the space of unimodular lattices is bounded. Okay, so bounded GT trajectory. Okay, so all right, so this this is Downing correspondence, and what else do I know about these sets? Well, I know, for instance, that this is a winning set, which I'll talk about in a moment. But winning in particular will imply a Hausdorff mission result. So this is winning, both of these things. This was done by Wolfgang Schmidt in the 60s, and I think this was done in Donnie's paper in 85. Okay, so they're winning sets. And what I want to tell you about winning sets is that they imply a Hausdorff dimension result and a countable intersection property. So I don't want to really define them because I won't use them in any real way. So AN is a winning set. I don't know. Oh yeah, this is a set of winning sets in some Euclidean space of some dimension. This implies two things for us. Okay, so that the Hausdorff dimension, I'm going to always use dimension to denote Hausdorff dimension of AN. It's going to just equal the dimension of X. Okay, so it has full Hausdorff dimension. And also what? If I intersect them, okay, there's a parameter associated with winning, if we forget that. If the parameter stays bounded, if I can intersect countably with many of them, this remains winning. Okay, which implies it has full Hausdorff dimension. So this is kind of a nice property, right? So it's not true that if I take full measure sets and I intersect them, I get anything, right? For instance, you can take winning implies this is full Hausdorff dimension on the real line, and its complement is the set of its complement is a full measure set, but the intersection is empty. Okay, so its complement is a full measure set which has full Hausdorff dimension, but the intersection is empty. So that's an example of two full Hausdorff dimension sets intersecting to give you nothing. Okay. All right, so that's pretty good. All right, so from dynamics, we're going to use some results. So we're still under non-dense points. Okay. All right, so in this setup, if I have a C2, well, let's say an Nosov. Well, okay, let me just say that this is a compact Riemannian manifold. And if my mapping is, say, C2 expanding or C2 Nosov, then there's a theorem of Rabansky that says that the Hausdorff dimension of the non-dense sets, the non-dense set, which is of course a set of points that have non-dense orbits in this space, then this is full. And this was Urbansky, I don't know, 91. So this is C2. For a winning result, I have an old one, where if we restrict to the unit circle, and I have some C2, then this is winning. Then and this is an old result of mine from 09. Okay, and so winning, of course, is stronger than full Hausdorff dimension because it has the other property. All right, so
What are the assumptions?
For what? For this?
For this.
It's just C2 expanding. No. So
Expanding.
yeah. Okay. Now, if we return to linear maps, and I want to do that because the rest of our talk will be about linear maps, then there is a result by let's see. So T going from the circle to itself. This is linear automorphism, linear endomorphism. Let's see, endomorphism. Then this set is known to be winning as well. So ND of T is winning. And so there are a number of results. So there's an early result by Donnie, but so let's just put the names here. So Donnie, 88. But the sort of statement here is from Kleinbach, Broderick, Fishman, and Kleinbach. So, and this came out in 11. Okay. So in particular, it says that for linear endomorphisms of the d-torus, the set of non-dense points is winning, so it has full house information. Okay. These are all, by the way, measure 0. The non-dense set, because everything's ergodic here, all the systems I've mentioned, so all the non-dense sets will have measure 0. So there's no point in talking about measure. All right. So in particular, if you're talking about linear endomorphisms, these are given by matrices with integer values. You can actually intersect all of them. You can ask for the points that are simultaneously non-dense under all of them, and that will also be winning and full house information. Okay. Any questions so far? Okay, so I want to mention one other result for non-dense. And the reason is that we're going to sort of need this. So it's, okay, so examples have been number theory and dynamics. These are not really rigid categories. I just organized them like this. So homogeneous dynamics. Okay, so here, if I have G be a connected semi-simple group, real, without compact factors, and gamma will be a lattice, irreducible, and AT will just be a one-parameter non-quasi-idempotent subgroup, non-quasi. Of G. Then there's a result by Kleinbach and Margulis that says the non-dense sets of AT, that this is Hausdorff mentioned, that the dimension of this is equal to the dimension of J. Okay, this is Kleinbach and Margulis in 96. Okay, so we're going to use this because we're going to talk about simultaneous dense and non-dense. All right. So let me tell you our results. Any questions on sort of the background before I do that? Okay, good. I have another board. Try using that. All right, hopefully this wire will not be a problem. Okay, so here are our results. Okay, so okay, I've told you about dense sets. I've told you about non-dense sets. Now I want to ask, you know, how big, if I take two different maps on the same phase space, what about looking at points that are simultaneously dense and simultaneously not dense? Now, if it's simultaneously, if two of them are simultaneously dense, we've seen if it's ergodic, it's easy. And since all of these things, many of these things are winning, we can also intersect simultaneously, we'll look at simultaneous non-dense points. So it's this mixed case that's not really amenable to the methods so far. And so this is what I want to talk about. theorem 1. Okay, so this is Ferguson, Exeter, and me, and this is going to come out. Okay. So what do we have? Let me just write the statement. So let's let T and S.
Jim,
Yes.
is that result, if gamma is co-compact, I mean, so they proved this for bounded orbits, right?
Yeah, that's right.
So this result is for gamma not co-compact, what you're saying.
No, I mean, non-dense orbits. I need that point to be. Well, if it's non-dense, it's going to be.
Of course, no. If it's bounded, it's non-dense. But I mean, my point is, if gamma is co-compact, bounded. I mean, you know, they prove the non-dense in the co-compact case as well.
Yeah, I think so.
Actually, I have a very general question, but I don't know, maybe it's better to postpone it to the end. Does it have some funny consequences for numbers?
What?
These theorems.
Sure. So, for instance, Downey's result has that the geodesic flow, if it's bounded, those numbers are badly approximable. So they're badly approximable.
Okay, but still, what's the relation with non-dense and dense?
Oh, yeah. There's no more number theory. Yeah. Okay. So let T and S be commuting for all the things I need. Well, for almost all of them, I will be talking about commuting. Hyperbolic toral automorphisms, such that, well, if I look at their joint commuting action, they will generate such that T and S generate a Z2 action without rank 1 factors. I'll explain in words what this means in a moment, but then the conclusion is, by the way, so, okay, let me write down some of these things. So the non-dense set for one of them, let's say P, doesn't matter which one, intersect the dense set for the other, that this has full Hausdorff dimension. Okay, so again, this set is not winning, so there are no winning, and this set is winning, so it's an intersection has no meaning in terms of winning. But it has meaning in terms of full Hausdorff dimension. Okay, so that's the first result. Now, through commuting maps, so they generate some Z2 action, and without rank 1 factors means that basically on any induced tori, these two actions don't become one powers in one map. Okay, because the reason is that, well, the silly reason is that if I take S to be a power of T, then this clearly will be empty. Okay. So that's our result. And then there's one for the Lie group case. I'll write that too. Oh, but let me write theorem 1.5, which is just me, and this also came out recently. So here, if I forget commuting and I stick to d equals 2, I have a geometric proof for a weaker statement. And so here, TS, they don't have to commute, but they're hyperbolic toral automorphisms on T2. And then, well, okay, if their contracting directions are, they don't coincide, Okay, then what can I say? Well, I can say that the dense set, that dense T intersect non-dense S for four orbits in this case is dense and uncountable. Okay, I'm pretty sure you can push this result to higher dimensions, but I haven't done that. Okay, so but mostly I will be talking about this result. Let me tell you the other result in this paper about Lie groups. Okay, are there any questions before I try to erase stuff? Okay, good.
So TNS are linear maps,
Yeah, they're linear maps.
but they don't commute.
They don't necessarily have to commute, or they can. No, they won't commute. Yeah. Okay. So the other result with so here's theorem 2. That little one was theorem 1.5. Okay, and it's with Vitali and Manford. So here I want G to be a connected. Well, it's the same condition as before, semi-simple real Lie group. Such without any compact factors, such that each simple factor has rank real rank greater than 2. Okay. All right. And then if I take A1 and A2 to be just elements of a maximal abelian R diagonal, I can't say this, R diagonal subgroup of G, such that, well, okay, I want, when I sort of, when I look at the Lie algebra elements corresponding to these things, I want them to be linearly independent in each simple factor. So the Lie algebra elements are linearly independent. And then, so then the induce action, the action, oh, yeah, what am I inducing on? So I need gamma to be a, so everything for this talk is about compact spaces. So this is going to be a co-compact irreducible lattice. Okay, and so if I look at the induce action on the moduli space, the idea is the same result. So then non-dense set of A1 intersect the dense set of A2 has full house result. Yes?
I'm very sorry. Could you please explain that line? Lie algebra elements are.
So if you take the Lie algebra elements corresponding to A1 and A2, then these are some vectors, right? And so I want them to be linearly independent when I project onto the factors, each factor.
You mean eigenvectors or?
No.
Diagonalizable subgroups, and there is one parameter subgroups contained in that.
Yeah.
So G is product of GIs,
Okay.
and then you look at AIs, you take the log,
Yeah.
and you get some element in the Lie algebra of this torus.
Yeah.
So when you project it to each one of the GIs, the assumption is that you are going to get two vectors that are linearly independent.
Yeah, so you don't want them to coincide because I don't want the action to be degenerate. Okay.
My
Oh,
experience with it is, it seems to me
So
very restrictive.
if it is simple, if it's just one factor, it just means that.
Yeah, that's like that. But if you have two factors, it seems very strange that they never fall however you turn them.
Okay, I assume that
It's not however
he's
you
going to
turn
work
them.
with each factor separately.
Okay.
okay. So we can talk about this later. But okay, so that's the statement. So what I want to do is I want to. Oh, and I want to mention that there's theorems 3 and 4, which I don't want to talk about today because they're still under preparation, and that's like joint work with Rangon Shi. The thing that we are considering is for when we have the non-compact lattice. Okay. Right. So I want to show you how to prove theorem 1. So proof, well, I'll put it in quotes. Proof of theorem 1. And theorem 1 was the result for the torus. Okay? Okay, so I should mention at this point that the technique, so we're building on results of Host and Johnson and Rudolph for the times 2 times 3 map, for instance. So what do I want to do? Let's just pick a point where in my torus. And this is the point that I'm going to miss. You can pick a finite number of these. It doesn't matter. Okay, just pick one. And I'm going to define the sets. Sorry, this will be x. This is easier to write that. So p to the d. Okay, so I'm going to just look at the set of points in my torus that whose orbits will miss something. Okay, so whose orbit, this is the complete orbit under the P map of this point. If I look at its orbit closure, no, okay, I don't want the orbit closure. If I intersect some ball of radius x naught, sorry, at point x naught of radius 1 over q, for instance, this is supposed to be empty. Okay, so this is a closed T invariant set. All right. Now, I said that Broderick, Fishman, and Kleinbach have shown that for linear endomorphisms of the torus, that the non-dense points are sets, the points with non-dense orbits, that set is winning. Okay? So that tells me in particular, what is this? This is a set of points in the space who are missing this sort of shrinking neighborhood of this point x naught, which is fixed. So as q gets larger, this is heading towards a set of points that are non-dense. Okay? So the house, in particular, the result implies that the Hausdorff dimension of this thing is very large. Okay, so I'm going to abbreviate their names. Steven, Broderick, Fishman, and Kleinbach imply that the dimension of EQ goes to the dimension, well, actually, it goes to D, Q goes to infinity. Okay, that's that. Now what do I want to do is I want to use the variational. This is a closed T invariant set, and I want to get a measure. So there exists some mu, which is a measure on EQ, supported on EQ. Okay, such that, well, what? Well, the variational principle tells me that the measured theoretical entropy of this can be pretty close to the topological entropy of this. In other words, there exists such a measure such that what happens? If I look at the topological entropy of this map with respect to EQ, restricted to EQ, this is going to be pretty close to the measured theoretical entropy of this map restricted to EQ. Why is this? Well, because this thing here, because of this entropy result, we can do a calculation which shows that this is pretty close to, I'm going to use this for pretty close to h top of t, because EQ is a very large fractal. And it's just a calculation. So then we can apply the variational principle to get a measure whose entropy is pretty large, and its support is on this. Questions on that?
What does H delta mean? H naught.
Each number, what do
New.
So you can, there exists X naught, not a lower than.
No, no. This?
So for any X naught, so can it be a point?
It could be any point. I can
But
pick.
it might be a point that is dense. It's like lower dense.
No. This is a fixed point. This is the neighborhood that I'm missing.
Yeah.
You're not looking at the orbit of X.
You're not looking at the orbit of X. This is X. Right? The orbit of X will miss this neighborhood.
A specific point.
This specific point, yeah. This result can deal with specific points. Okay. So now what we need to do is to average.
Yeah, I'm sorry, is it obvious that the dimension is somehow continuous in this sense?
It isn't, but so if I take a filtration of sets, the Hausdorff dimension, the union of those sets will go up to the Hausdorff dimension of the big set. Right? So in other words, so the union. Sorry. So each of these is less than whatever this is. We're talking about dimension. And then there's a standard result that says that if I take, if this is everything, then the Hausdorff dimension goes to that. Okay, so I'm just covering this union. So you eventually have to get all of the dimension. All right. Okay, so I want that average. So I'm going to define another measure, un. Okay. And just what I want to do is I want to take the measure that I just found using the variational principle, and I want to average it with respect to the other map. Okay, so it's this. Okay, that's just the, push forward of this. Okay, so I just have this so far, and well, all these measures are going to be t invariant, and because t and s commute, they're going to also be, and they're also going to be s invariant. Okay, so in particular, that implies this for the limit measure. So what I'm going to do is erase this. Okay, so then just take a weak start limit along some subsequence. Okay. Okay. Then the limit measure will also be t and s invariant for the same reason. And then now we use measure rigidity, which is the result of Ziegler and Lindenstrauss measure rigidity. I can't spell rigidity. Okay, so rigidity. And this is the 03 result. And what does it say? Well, it says in particular, I won't write down the whole entire theorem, but it says that when we have, in this torus case, if I have two commuting actions, and without a rank one factor, so exactly the condition before, if T and S form a Z2 action without rank one factors, and the measure mu is both T and S invariant, and it's an ergodic probability measure, then the only, well, maybe I will write this, it's just too confusing. So T and S commuting, as before, such that TS okay, so this is my algebraic Z2 action. I'm just writing it like this. All this means is this, actually. Okay, has no rank one factor. Okay? And so if I also have a measure, so what is my measure? So if mu is a TS invariant, so it's a jointly invariant ergodic measure. On TD. And so here's the entropy condition. So with the measure stroke entropy of, I just need it for one of the maps, so I'm going to pick T, okay? To be, okay, I don't really want to state the right condition, so to be pretty close to the topological entropy, okay? Then the only possibility for measure is Hahn measure. Mu is Hahn measure, so mu of x. Close, so what happens to the entropy is that it can possibly get trapped on induced tori, but it's quantized. So that when you get above a certain fixed point with respect to the fixed amount, then it can only be full entropy. Okay? No, we're going to take an ergodic component. Okay. Right. So the upshot is that, again, measure rigidity, this theorem, and ergodic decomposition tells me that I have what? That this week's that mu has to have an ergodic component, or I'm going to just assume that mu is ergodic, and it's therefore going to be a Lebesgue measure on X. Okay, clear so far?
Mu there, T invariant?
This name, yeah, because well that comes from the variational principle, because EQs are T invariant. You can just do, it's a small calculation.
Yeah,
Okay.
sorry. How do you know you don't lose entropy by going to the body component?
How do we know we don't lose entropy by going to? Okay, so I have this thing. I apply measure rigidity. Oh, there's another calculation that we show that the component that comes out. So if you do this without the ergodic condition, we get a component that has to have positive mass, and that will be ergodic, and then therefore it will be Hahn measure. Yeah, I'm just hiding that detail. Other questions? Okay, so the upshot is that the measure nu on this set. Okay, maybe I will erase this.
Would you repeat actually your answer? I didn't get it.
Yeah, so there's essentially a calculation that we have to do to show that the component we get has positive mass, and so that component is, we can think of it as ergodic.
Positive mass is it?
Hmm? So if you don't assume it's ergodic, you just let this go through, we get a component that is going to be this. And we just
And
show
when
that.
you don't, I mean, how do you know that it has max entropy, that component? That was the question.
Yeah, there is a calculation that we do to show that. Yeah. Right. So, okay. Right, so there's a couple more calculations. I don't know how much of it to do. All right. So the upshot of measure rigidity in ergodic decomposition is that the measure, which is supported on these EQs, right, of the dense set, this is full, and this is also a calculation that you have to do. So we can, by decomposition, assume that this is ergodic. And so the idea then, let me just summarize this so we don't have to write it down. The idea is that if this is false, if if this is a zero measure set, then I look at the non-dense orbits, and I will somehow decompose this into a finite disjoint union of sets, and I will restrict my measure nu to it. Then I will do the averaging process again, and there, by measure rigidity, we're going to get Haar measure on a component. But the problem is that if the non-dense sets, if they have full measure, then since it's non-dense for the map S, that tells me that I will not be able to see some neighborhood of a point, and so that will give me a contradiction. But anyway, this is another calculation. Okay, so that tells me this. And so now what do I need to do? I need to, let's see. I have a measure supported on this fractal. Okay, that's all I have, and I know that the measure of the set that I want with respect to this measure is full. So I need to convert this to a Hausdorff dimension result. So then here we use the Tropier-Young formula. All right. So what does this say in this case? I won't say it in the most general case, but it's for C2 maps of Riemannian manifold, compact Riemannian manifolds. So, and well, this is one of the reasons why we tend to need to have compactness. We have to use this. Okay, so what? So I'm going to so it's the same setup. My map is T. I have a torus. I'm going to let kappa j, j going from 1 to u, be the positive Lyapunov exponents of my map. So in this particular case, what are they? In this particular case, they're just the log of the absolute values of the eigenvalues of T, that are positive. Okay? So I have this. Okay. And then the conclusion, so once you have this, then the conclusion of the formula is that, well, there exists some numbers, gamma I, between 0 and this thing, dimension of EI. I'll explain what this is. So this is the dimension of the tangent space at some point x. Now I can't take all points. I'm assuming my measure to be organic, so I can take almost all points. But since I do that, I'm going to just ignore putting this at a point. So in other words, this is constant almost everywhere. And so I have this number between this and that. So tangent space corresponding to kappa, okay, I'm going to call this J. Everything's J. Okay, so these numbers exist. And so such that, what happens? Well, there's two things. One is that the pointwise dimension, I'll define this in a moment. The pointwise dimension of the unstable manifold is equal to J. Oh, okay, so yeah, this is U up to U of these gamma i's. Okay, that's the first conclusion. The second conclusion is an entropy result.
I have one more better question. What are these lean exponents that you mentioned?
What was that?
You mentioned let kg be the positive lean exponents.
Lyapunov? I didn't want to write the whole name. There's just a Lyapunov exponent. There's a dot here.
Okay, so they correspond, there's Lyapunov exponents?
They're just the logarithm of the absolute value of the eigenvalues of T.
Oh,
Okay, I should say for T. Okay, right, so we have this, and then so the second result is that the measure of theoretic entropy of respect to my measure nu, that this is going to be equal to mass T. This is going to be equal to the sum j going from up to u of the Lyapunov exponents times these numbers times sort of the local dimension, pointwise dimension. Okay, so that comes from this formula. All right, so what do I want to notice is that now the topological entropy, so the topological entropy is this. So H top of the system, this is just equal to the sum up to u of the Lyapunov exponents of dimension Ej. Okay, this is a fact. Okay, and so what this formula is telling me is that these gamma u's, so since this thing, remember what we did was we constructed this mu in such a way that this is fairly close to this, right? So that's telling me that this gamma j is pretty close to the dimension. So that's pretty good. And now what is the definition here? Let me recall for you that definition. So delta mu, this is defined to be the limit as epsilon goes to 0 plus of the log. Okay, so in their paper, they construct conditional measures on leaves here, situated at a point, so mu. So I need to use that conditional measure. Okay, but it's okay for almost every x. So if I look at this ball, this over log epsilon. So that's what this is. And remember, these things are equal to that. And so by this calculation, this is supposed to be equal to the sum of the dimensions of the tangent spaces corresponding to Kj, and they sum up to the dimension of the unstable manifold. Okay? All right, so then I just need to just convert this using the mass distribution principle. Which will tell me what? Which tells me that the dimension of ds, which is that set term, living on these closed p-invariant sets that we have, these in the unstable directions, this is bigger than or equal to well, okay, so. I don't really, if I take a limit as the other thing goes, as q goes to infinity, we'll get this, but this is bigger than this. Okay, which is again just the sum of the local dimensions of the unstable manifold. Which is yeah. So here I'm getting a dimension result now. Okay. Now what I do, I'm almost done. So what I need to do is now, T is an automorphism, so I take its inverse. And I do the same thing again.
What's the last?
Mass distribution principle.
You said what that is.
Yeah, sure. So so when this happens, so when nu of b of x of epsilon is less than or equal to c times epsilon to this. Well, this is what this is saying, right? When we have this, this implies a result for Hausdorff function immediately. Okay. So I have this. Right now I look at the inverse, and then there the unstable for the inverse is the stable for the original map, and vice versa. And so I'm going to get the same result, but for this, where I replace S stable by unstable by stable. And so I have these two Hausdorff functions on the stable and unstable manifolds, and there's a local product structure. How much time do I have left? Okay. There's a local product structure Okay, so let me write down what I said in words. So then do for the inverse, and you get what's the dimension of ds intersect dq intersect the stable. Oh, all right. Let's not do this. U.
Actually, sorry, just when you put this in the quote, when you answer the question, when you put in the quote on the ball, the measure of the ball is bigger, right?
No, I think that's correct, right? That
You get
direction is correct.
a lower bound of the dimension from that. How can you get lower bound of the dimension from the lower bound of the measure, from an upper bound of the measure?
Well, that's the standard result, right? So
Use it to cover your
yeah,
cover
Okay.
you
space.
use it to cover. Yeah, it's not that needed. Okay,
Tells
so
you that the S dimensional measure is bigger than or equal to something.
okay, so reversing, you get this, and so now I need to put it together. It's a local product structure. Which we can use with a little bit of calculation, the Marchand slicing theorem, which allows us to put together Hausdorff mention on a local product structure. And so that tells me that I get this. So dimension of ds intersect eq is, okay, so again, there's a local product structure, so the theorem gives me du plus ds, and this is just a dimension, this is just d, right? Because it's the hyperbolic total automorphism is an also. Okay, so, sorry, this isn't d. I should be a little more careful, okay? Now what I want to do is I want to let q go to infinity, and that becomes d. So when q goes to infinity, these sets get higher and higher Hausdorff mention, and so this becomes d. Okay, so that is an outline of the proof. Are there questions on that? So this is why I say that we don't use winning anyway, because it doesn't come in. Let me say one more thing about a corollary then, since I have like a few minutes. We can also, maybe I'll write the corollary here. All right, so what are the corollaries? Well, the corollary is this. So I have t, okay, which is, everything's going to be on the detours. And then I'm going to take some, say all maps, all hyperbolic total automorphisms, Sn, such that such that individually t Sn generate the conditions of the theorem, generate a Z2 action without rank 1 factors. Okay, so then we can conclude that the non-dense set for T intersect all of the dense sets for us. Right? Okay, so N, this has full Hausdorff mention. Okay, and that's because, again, all we're doing is right there where we constructed that measure. If they satisfy the theorem, they're all going to satisfy that. So I can just take the intersection over all of them. Okay? And then everything else works in the same way. Okay, so that's the corollary. So this leads to a question which we don't know how to solve. Is that we know if I take another map, say T tilde, and I look at the non-dense set for T and the non-dense set for T tilde, I can intersect them. They're both winning, right? You get a full Hausdorff mention set, but I can't show that if I try to intersect this again with T tilde that I get, well, I don't know what I get. I mean, I suspect it'll also be full house recognition, but this technique will not work because once I have another set and I consider, okay, the reason this technique, current technique, I don't think will work is these sets EQs, which I've erased, this thing, is T invariant, but it's not going to be T prime invariant, right? So once I try to move it around with T prime, that's like, you know, that's exactly what I do with S. And so this, as far as I know, we cannot get it to show the stronger thing. So that's an open question. Okay, are there questions? Okay, well, let me stop here and take questions.
I have the same question. What are the applications to number theory?
No, I said there aren't any, as far as I know. This is not a number theoretical result. I mean, it's
No,
some
I
of it.
imagine there are some, well, you can
Well,
say
okay,
it's
I
some
mean-
funny translation. I just wondered. Maybe you said you can.
Well, okay, we haven't thought of any number theoretical applications of this. There could be. I shouldn't say there aren't any. We weren't thinking about this because it's not something we talked about. Yes.
Now, in this theorem, which is just by yourself and you have non-commuting maps.
Yeah.
Do you use some sort of binary con instead of non-unity?
No, so I use that's quite easy. It's very geometric. So eventually I end up using the bare category theorem to get that result. So what happens is I have this fractal set again, and so what I do is in the other direction, it's gonna not coincide. I just wait to see how often it returns, and I pull everything back, and then you'll see after an intense computation that you get it falls into the scheme of the bare category theorem. So you get a dense uncountable set from that. Yeah. So in theory, since they're not related, they're less related if they're not commuting. This should certainly be true.
Can you do anything like, so if instead of looking at these dense sets, right, so suppose you took the shrieking target set, right, where you had some full measure set, but you had some a rate on these sets, or you know how well they affect rather than.
Okay. Oh, so you want to ask a similar
so,
question?
So you know you take
that.
with some map you have some non-dense.
Sure. I mean, that's a very good question, and we thought about doing that a little while ago, but we haven't really thought much about that. But it would be another refinement here. I don't know if what we have will work. It could. I just haven't thought about it.